Okay, now we're going to look at slope fields, and they have to do with the differential equations from last section. So if you're given a differential equation, remember that means an equation that's really a derivative, and we want to take a look at what graphically it might look like. So maybe we can't solve it, solve the equation to get to our particular solution, but we just want to get a sense of what the graph looks like. A slope field will give us that sense, and it's going to show us a family of curves. So it's not going to show us any one particular solution because we haven't solved it. It'll just show us the trend kind of for all the family of curves. We can get an idea for the shape of the curve, and whatever shape you're seeing, like I said, you'll see the same shape over and over. It'll just be shifted up 1 or down 1 or up 5. So that's what we're doing here with the slope field. And if I give you a differential equation, can you kind of sketch a slope field? If I give you a slope field, can you come up with the differential equation? We're going to kind of go in both directions. So some things to remember here. You can pause the video and read. I'm not going to read these to you. Okay, so welcome back. I kind of explained what they set up there. What I have typed out. So let's do what they're asking us to do here, which is a little bit of practice from last section. We want to solve the differential equation. So if I separate the variables, I then integrate both sides. So the integral of dy is y. I apply power rule. I get 1/2 x squared minus x plus c. They didn't give us initial conditions, so all we have is our general solution, which means it's got so we would say it's the general solution of the differential dy dx. It's got the whole family. That c value can be anything. So we'll say the explanation is that the plus c means that there can be an infinite, or I should say there is, it's not can be. There are an infinite number of solutions as the shape of the graph would be the same. Whoops. It would just be shifted up or down. All right, so here's a differential equation. Let's get an idea for the slope field. So we're going to find the slope for each point here on this graph and make a small mark that's going to represent the slope of the graph or the slope of the tangent line to the graph at that point. And what will happen is, like, if we start to see slopes that do something like this, if our slope field starts to look like that, we can kind of say our solution, our general solution will look like that, and we'll see slopes, right? It would just kind of do the same thing. We're going to see something like that occur eventually. That's what we're going for. So once we have our little slopes drawn, we can kind of start to visualize what the graph might look like. So what I'm going to do is I'm going to start with this point here up top, which is -2, 3. So the slope, let's make a table of values actually. It's probably going to be easier. So at the point -2, 3, if I plug it in to the equation, well, there is no y to plug it into, but if I just plug in the x, I get a slope of -3. So at that point, I want to draw a slope, and you might want to use a ruler. You make a small little line segment that represents the slope. That to me would be -3-ish, right? Because if I go down 1, 2, 3, and over 1, 1, 2, 3, and over 1, I'm sort of visualizing that. If I continued that down through there, it would be about that steep. So that's how I'm kind of, if you're having trouble visualizing it, I'm trying to think of -3 and then just draw a small segment for that. Okay, now if we try the point -2, 1, Again, there's no y to plug it into, so when I plug in -2, I'm still getting a slope of -3. So that's going to happen for any one that, because there's no y in our differential, all of these x's are going to have the same slope for this example. Those are all going to have the same slope of like -3 because there's no y in there to change it, right? So now let's move over to the next point, -1, 3. If I plug in a -1, I get a slope of -2. So now I'm thinking down 2 and over 1, so it's a little less steep. And all of these are going to have that same slope. And I'm aiming at going down 2 when I draw it. And over 1. So they're a little less steep and they're in the negative direction. I know they're all the same because the y is not really affecting it. Then when I plug in 0, I'll do 0, 3. I get -1. So now I'm thinking, at this point, I'm thinking down 1 over 1. -1 is going to look like that. It's that nice 45-degree angle. Those are sort of easy to sketch. I'm pointing it right down at the next point below it. All right, and then now let's plug in 1, 3. If I plug in 1, I get a slope of 0, and that'll happen for all of these. Those are also pretty easy to draw. This slope of 0 is going to be key to helping us with a lot of these questions that they ask. Remember that when your differential equals 0, you're getting little slope segments that are horizontal. And then lastly, when I plug in 2, it doesn't matter what y I plug in, I'm always going to get a slope of 1. So now I'm looking at a positive slope that would go right down to that next point right there, right? So that's how I kind of figure out or estimate the slope. So you have to be kind of good at estimating what the slope would look like. And I tried to show you a method, if you're not that great at it, how you can do that. All right, so that would be our slope field. And I can get a general sense of these curves through here. It looks like if I kind of follow the tangent lines, whoops, it'll do something like that. I can sort of see parabolas taking shape here. And that would make sense because if I integrated a power of 1, I would get a power of 2, which would be a parabola. So there's our slope field, and it gives you a general sense of what the general solutions are looking like. So that's what I'm pointing out down here. All right, so let's try another one. So here's our new differential. Here's one where x and y will matter kind of for each point here. So again, you got to make a table of values. I'm going to leave myself some space in case I need another table over here. So we're going to start with the point -2, 3. If I plug that in, whoops, I'll do it over. I'll start with these over here. -2, 3. If I plug that in, I got a -2 minus a 3. I'm getting a slope of -5 for that guy. So I imagine if I'm at this point and I go down 5, 1, 2, 3, 4, 5, and over 1, if I drew this line all the way down there, that would be pretty darn steep, right? So I'm trying to kind of get that feel for a really steep slope. That would be a slope of -5. Now what happens is if I do -2, 2, I get a slope of -4, so it's going to be not so steep. I mean, I don't know if you can tell that it's kind of flattening out, but if I plug in -2, 1, what do I get there? -2, 1. I plug in that and I'll get a -2 minus 1. I'll get a -3. So 1, 2, 3. It's still kind of pointing at that, but you can see it's flattening out. And I go -2, 0. I get -2. Again, I'm going down. I'm aiming for like down 2 and over 1. So in this case, I'm always aiming at that same point. Then when I plug in -2, -1, I get -2 plus 1. Oh, I should be writing these in. Sorry. -2 minus 1 was -3. -2. -2 minus 1, I'm getting a -1 slope. because it's going to be negative 2 plus 1. So you can see them flattening out. And then negative 2 would be negative 2 plus 2. I would get a slope of 0. I would get that horizontal segment. I'm going to ask you to pause the video here and do these on your own and see if you can get your slope field to match mine. Okay, so your slope field should look something like this. Again, if you're having trouble getting it, you can ask me about it in class. Okay, now it's the reverse question. Shown below is a slope field for which of the following differential equations. Explain your reasoning for each of the choices below. So there's a couple of ways that you can do it. I like to think about 0 is helpful a lot of the times. And we just start eliminating choices. So I know that when dy dx equals 0, I'm going to have a horizontal line tangent segment, I'll call it, at those points. That's one method. Another method is to just pick a point that's really not horizontal, just one point. Like I can look for a pattern in the horizontals, or I can just pick a point that's not a horizontal, because that'll make it a little tricky. So like if I pick, for instance, this point right here, that's the point 0, 1. I can plug that into each of my differentials and rule them out. So if I plugged 0, 1 into this first guy, I would get 0 times 1 is 0, and I could see at that point my tangent segment is not 0. If I had to estimate, it's like 1 or 2 or something. It's like a positive 1 or a positive 2. So it's definitely 0, so A is right out, Renee. Now if I go to B, I choose that same point 0, 1. If I plug it in, I've got 0 times 1 minus 1. So I get 0 minus 1. I'm getting a slope of negative 1. That's clearly a positive slope. It's not a negative negative slope. So then B is right out. For C, if I plug in the point 0, 1 and see what kind of slope I get, if I plug in 0 and 1, I get 0 plus 1. So I'm getting a slope of 1. That's a possibility. Maybe. I'm not going to cross it off. I can't tell if that slope's really 2 or 1. Now if I plug in the point 0, 1, I get 0 plus 0. I'm getting a slope of 0. So then D is out, because there's no way that that slope is 0. It's not horizontal. And then if I plug in 0, 1 into this guy, I get, there's no y value, so I just plug in the x value of 0. I get 1 cubed is 1. So this is still a possibility. So now you'd have to pick another point. Because this has a cube, I might pick a negative slope somewhere. So I might try like this point down there. Now that's got a slope of, say, negative 1 or negative 2. So if I use that point is 0, negative 1. If I plug 0, negative 1 into that bottom guy, I'm getting a slope of, again, I'm just plugging in 0. I get a slope of 1. And this slope here is clearly negative, so I can throw that guy out. If I just double check my 0, negative 1 slope, I plug in 0, negative 1 in there. I get 0 plus my y, which is negative 1. I'll get a slope of negative 1, which, yeah, that could be a slope of negative 1. So it looks like C is my winner. That's one strategy. You can pick a single point. I would not pick one that's horizontal or vertical. That'll eliminate some choices. If you still have more choices left, pick another point that's got a different slope from the one you chose originally and start eliminating that way. One method. Another method is think about what I just said up here at the beginning. This is the other way. If you just think that anywhere where the derivative equals 0, I'll have a horizontal tangent segment. So if I say 0 equals xy here, my solutions to that will be any x's anywhere x is 0 and anywhere y is 0. So any points where the x coordinate is 0, my slope should be 0 for this differential equation A. So if I go to the x coordinate of 0 and I look all of these points here, these are all the points that would have an x coordinate of 0, right? 0, 5, 0, 4, 0, 3, 0, 2. And if this were the equation, anytime x is 0, I would have a horizontal tangent segment, right? Because that would make the derivative 0. And that's clearly not the case. Those are not horizontal, so I can rule that guy out. If I say this 0 is equal to xy minus y, it's hard to find the solutions as is. I'm going to factor out a y. So now I know my solutions to this are y equals 0, x minus 1 equals 0, so x would equal -1. So this means any points where the y is 0 would have a horizontal tangent, and any points where the x is 1. Well, let's look at points where y is 0. Y is 0 at all of these points here, right? Got -5, 0, -4, 0, 1, 0, 2, 0, 3, 0. These all have y values of 0. And all their tangent lines are horizontal. So that means so far this function's pretty good because I have my derivative equaling 0. Other solutions to this differential would be any points that have 1 for an x value. So that would be all these points here, 1, 1, 1, 2, 1, 3, 1, 4, 1, -1, 1, -2, and so on. All of those points would have a derivative of 0, which they clearly don't because they don't have horizontal tangent lines. So I can throw out this guy. So thinking about a tangent line of 0 helps. Here, if I factor out a y, I get x plus 1 equals 0. I'm setting my tangent lines equal to 0. If I solve this, it would be where y equals 0 or x plus 1 equals 0, so it would be x equals -1. So any points that have y equals 0, we already saw that works. That's all these points. And then any points where the x coordinate is -1, that's going to be these points, should also have horizontal tangents. So it looks like this guy's the winner. We can just check the rest of these. If I factor out an x, I get y plus 1 equals 0. So that's going to be all the points where x is 1 and where the y is -1. Let's see if I have horizontal tangents there. Along the line x equals 1, no, those are not horizontal. That one's out. This last one, if I say 0 equals x plus 1 cubed, that will be for any x's where, so if I solve that, I cube root both sides, I subtract 1, it would be x equals -1. So it would be here, and that looks good. But then we also have, the trick here is we have more horizontal tangents here where it doesn't come up because there's no y in there. So that's why we would rule that one out. Or I could just say, yeah, my little 0 trick works for both of these, and I can narrow it down to 2. So I could say it's either C or E. I know it's C already because we already did it. So then at this point, when I have it narrowed down to 2, again, I would go back to just picking a point, like say right here. As long as it's not a horizontal. Pick one point, try it for both, and see. So that's sort of our method. Find what x's have horizontals, and then if you narrow it down, pick one point, or you could pick the one point from the beginning. It's sort of up to you, but that's the process on how we do that. All right, so let's look at some of our FRQs. How many do we have here? We've got 2 of them. All right, so we're going to go through this guy first. So part A, I'm going to have you sketch the tangent lines at all 12 points and pause the video and do that and see if you get it right compared to mine. Okay, welcome back. So there's the slope field. Again, you can ask me in class if you're not getting what I get. Part B. While the slope field in part A is drawn at only 12 points, it is defined at every point in the xy plane. So there's all the points in between. We're just showing some key ones to get an idea. Remember, it's like all these points here in the plane. I can draw slopes then if I want. They're all there. We're just looking at some kind of key ones. Describe all points in the xy plane for which the slopes are negative. So here you're just sort of analyzing your x to the 4th, your differential. So I see that it's factored, it's multiplication. So when would this be negative? If I'm multiplying two numbers, when either one is negative, like if one's negative and one's positive. So you got to kind of figure that out, which can be tricky with the combinations. The reason it's easy, and if they're going to ask you a question like this, they'll probably make it turn out like this. You have x to the 4th, which means this is going to always, for all x values, turn out positive, except at 0. You got to watch out for that. When x is 0, that's going to make this factor 0, which is going to make the whole thing 0. So we're kind of doing a sign analysis here, right? And if the whole thing is 0, it's no longer positive. So whatever solution, whatever answer you're going to come up with here, you do have to mention except when x is 0. And then, of course, over here, what would make this one 0, y equals 2, would make it 0, right? So we're going to remember that we have to exclude when x is 0 and y equals 2 from whatever our solutions are. We're going to kind of hold on to that. Because if I want to say they're positive there, they're not. It's going to be 0. So now if the first one is always positive for all other values of x, then we just really can focus on this. We want to make this negative, because then a positive times a negative will make my slopes negative. So if I want y minus 2 to be negative, I could say y minus 2 has to be less than 0. That's how we write negative. If I solve that equation for y, or inequality I should say, I add 2 to both sides. I get y is bigger as y is less than 2. So any points that have y values less than 2, that means that the slopes will be negative. I don't have to worry about excluding y equals 2 because that's not even in this set. Y is less than 2. So we're going to say the slope will be negative at any point x, y, and now we'll give our conditions such that y has to be less than 2 and x cannot be 0. Those are our conditions for x and y. All right, now we're going to do part C. Part C says find the particular solution to the given differential equation, and they give us our initial conditions of 0, 0. So I'm going to remember those. So we've got our dy over dx equals x to the 4th times y minus 2. Step 1, separate our variables. So dy equals x to the 4th dx, and I'm going to say it's 1 over y minus 2. Kind of did a couple things there, 2 steps at once. I multiplied both sides by dx. I divided both sides by y minus 2. When I integrate both sides here, I see this as a reverse chain rule. Because my denominator has an outer function of 1, I'm thinking natural log. If I take the derivative of the inner function, y minus 2, I get 1 on top, so that's a u prime over u situation. So the integral of that is going to be the natural log of the absolute value of y minus 2 equals, on the other side we have power rule, 1/5 x to the 5th plus c. This looks familiar. I think we did this one before. Let's take a look. Right, wasn't this somewhere? Here we go. So I'm not going to go through all this again. We did it in a previous video. If you can't get there, let me know. But the final solution will be the one here with, we got the negative there, the 2 minus. This was in our previous notes. Let's see here. I'll do this. I'm cheating. I know. It's for everyone's good here in the video. Just looks familiar. So from here we'll go, whoops. From here we'll go up there. All right, so there's our particular solution. And that was part C, right? Cool. That was nice. Okay. Let's look at our next one. So consider the differential equation on the axis provided, sketch a slope field. So I'm going to have you pause the video and do that. I'll do the same, see if our answers match. Okay, welcome back. So you should get something like this. Part B, they want the particular solution with the initial conditions 2, 0. So I've got dy over dx equals y minus 1 over x squared. So I separate my variables, and I've got dy, whoops, dy times x squared equals y minus 1 times dx. I divide both sides by my x squared and my y minus 1, so I got 1 over y minus 1 times dy equals 1 over x squared dx. They love this natural log one here, so by now you should kind of recognize this looks like a u prime over u situation because my inner function is to the power of 1. That's what tips me off to that it's probably natural log. And the derivative, I don't have to mess with any constants because the derivative is 1. So it's going to be the natural log, the absolute value of the inner function, equals power rule on this side. So we'll bring that x to the negative 2 up. So I'm going to get the natural log of y minus 1 equals x to the negative 1. So it's going to be negative 1 over x plus c. All right. So that. Good news, I think we did this one before. So we're going to go snag that again. We're going to cheat. If you want to do it again for practice and see if you can get the answer, that might not be a bad idea. So we get this thing here. Oh, I should have a plus 1 in there. All right, because this was our solution when I solved for y. This was just my check, so I can pick the proper one. Yeah, so let's just grab this thing. You can do it again on your own to see if you can get there. I'm cheating, I know. All right, so there's our particular solution. Keep in mind, like a lot of times you'll see it written like this. So either way is acceptable. So that is part B. Now for that particular solution, they want us to find the limit as x approaches infinity of that thing. So remember doing the exponentials, the limits as x approaches infinity. We could try direct substitution. So it's e to the negative 1 over x plus 1/2 plus 1. So this was the whole idea. Just to give you a quick refresher, when we're plugging infinity into an exponential, if we have a number bigger than 1 to the infinity, that goes to infinity. If we have a number less than 1 to the infinity, that goes to 0. If we had a number bigger than 1 to the negative infinity, that goes to 0. Because what we do is we think of that as really 2 over 1. And by our properties of negative exponents, I can make my exponent positive if I reciprocate the middle. So then it just becomes the same as that guy, right? And then if I have a number less than 1 to the negative infinity for the same reasons, I could rewrite it as 2 over 1. Now it's bigger than 1 to the infinity, so that goes to infinity. Remember all of those rules. Actually, it's not even going to apply in this one. But that was okay. Good review of that stuff. And then like if we had a plus 1, it would just shift it up 1 or whatever. Yeah, I didn't need to do that, but okay. When we try direct substitution here, let's see what happens. Why I'm saying I don't need to do that. If we plug in infinity, basically we have negative 1 over infinity plus 1/2 plus 1. This thing right here goes to 0 because that's another thing we talked about when we were doing limits as x goes to infinity. If I have like 1 over x and that goes to infinity, the bottom just gets bigger and bigger and bigger, like 1/10, 1/100th, 1/1,000,000th. It doesn't matter if there's a negative on top or what constant's on top, because it's still just going to go to 0. If it's a negative, it's just coming in from the bottom of 0, from below 0. So that part's going to 0. A constant over infinity is going to 0. So this is really like negative e to the 0 plus 1/2 plus 1. So now it's like negative e to the 1/2 plus 1. And that's our limit. You can write it a couple different ways. Again, answer keys will probably look like that because that's cleaner. Actually, probably have a square root on there because e to the 1/2 means square root. Any of those answers are acceptable. That is our limit. Are we done with these notes? We are. Under a half hour. Nice.